So we're going to go through applying exponential regression models. So you guys were asked to build a chart that dealt with the year, which is modeled on this graph, okay? And then the number of years since 1860, okay? So the first year being 0, okay? The second year in 1870 being 10. And the whole reason we're doing that is because we're going to be replacing the x-axis here with new values. These will become our new values on the x-axis. And then you were supposed to find the world energy consumption on this graph. So you were supposed to estimate where it was. So I'm going to go to the next page here. So hopefully you take a good look at this graph. Go about estimating what you think each value is. Okay. On the next page, we've made a whole bunch of estimates with that graph. In fact, what I'll do is I'll pin that graph so that we can see it. Okay. Here we go. So here are all of our estimates from that graph. 1860, we figured we're at 0 and 1, and everyone's estimate is going to be a little different. What we're going to try to do is we're going to try to fit an exponential model to this, and then we're going to kind of superimpose what that model would look like on top of this graph. Okay? So we're going to focus on this chart page now. First ratios will let us know if something is exponential. And if you guys remember, we'll go to a single page display here. If you guys remember, our exponential model is written as y equals a b to the power of x. B is our value that we find in our first ratio. When we go through this, our first ratios aren't going to be identical, but we're going to try to find one that we all agree would be best. Okay? Our a value is when x is 0, what we start with. So it looks like our a value in this case is 1 from what we assume. So already we know our exponential model is going to read y is equal to 1. And we just got to find a value for b by going through first ratios. So I want you guys to kind of try to help me out here as we go through these first ratios. We take the second number and divide by the first. So 2 divided by 1 gives us 2. Excellent. Then we go 5 divided by 2. That's right. Then we go 7 divided by 5. What is it? 1.4. Okay. 25 divided by 7. 2.6. Good. Sorry, 3.6? Yeah, that's right. Scroll down a little. So we're going to try to go through these quickly. 40 divided by 25. 1.6. 49 divided by 25, almost 2.
40, like 40?
Oh, sorry, thank you, Sam. By 40. 1.2. 50 divided by 49. What is it?
1.02.
Yeah. Okay. 53 divided by 50. 1.06. 80 divided by 53. 25-ish. Okay. 125 divide 80. 1.56. Thank you. Let's scroll down. We're almost done here. 235 divide 125. 1.8. 295 divide 235. 1.25. Great. 380 divide 295. Anyone got a value for me? What is it? 1.28. And then our last one, 398 divide 380. 1.04. Great. Okay. Here's what's important. I want you guys to realize that, look, our first ratios were by no means identical, but we're trying to fit an exponential model here. So we're going to do our best to estimate what we think a good b value would be. Okay? So at some points, we're at 2, we're above 2. And then at most of the other points, we're below. And in fact, we go almost to 1. So one way we could do this is add them all up and find an average. And that's probably not a bad method. But that's going to take us a bit of work. So let's try to guesstimate right now and see how good our estimate would be. What do you guys think would be a good number to use as our B value from looking at this? Where do you think is going to kind of fall in the middle?
2.
2?
No, 1.
I feel 2 is pretty high.
1.6.
1.6, 1.5. I think those are both pretty good estimates, okay? 1.56? Okay, let's just go to one decimal place here. So, because it's relatively easy to work with, let's go with 1.5 as our B value. Okay, so we're going to extend this page and go down. So what that means is we're estimating the model to read y is equal to, remember it's a b to the power of x. We're estimating our b value to be 1.5 and our a value to be 1. You got it on the desk? Okay. And the b value is to the power of x. So, what I want to do is I'm going to show you guys the next page here. Let's unpin this. Let's show you guys our next page. Jump over a little. Okay, so what I have here, I know it's a little hard to see, but I've kind of made our old graph transparent. And what we're going to do is we're going to try to fit our new model onto this graph. And we're going to see how well the model fits that we estimated. So let's go to single page. Here it is. And again, if you guys recall, these are all the years from 1860. So this is when x is 0. X is 40 in the year 1900. X is 80 in the year 1940 and 120 in 1980. We're going to use these 4 points into our equation, plot them, and try to fit a line through it to see how well it superimposes on what we had. So, again, our estimate was y was equal to 1 times 1.5 to the power of x, right? Our first value is when x is 0. So, very first coordinate we go to find, y is equal to 1 times 1.5 to the power of 0. What is 1.5 to 0? The exponent 0. Anyone know? Just 1. So this becomes 1 times 1. Our y value is 1. So when x is 0, our y value is 1. That looks like a pretty good fit to start. Okay? Let's take the next x value when x is 40. And again, we're going to need a calculator for this. So our second coordinate, y is equal to 1 multiplied by 1.5 to the power of 40 this time. Okay? Now I'll take a calculator out.
7, 12, 5, 7, 3, 3, 2, 4, 3.
It is a huge, huge number here. Let me double check that number. Whoops. What we discovered is this ends up being a number larger than 11 million. Obviously, from what we have, this is going to be a terrible model. At 40, we're going to be way, way up. So let's go back to our drawing board. Okay? Maybe 1.5 is not a very good fit.
10 years though. Is that right?
That was over 40 years.
Right.
Yeah, so it's a very large number. So let's think of a better model here. At one point, if you guys notice,
But couldn't it be to the power of 4 though? Because to bring up the 10 years.
oh, maybe, sorry. Okay, sorry, I made an error. We're going through this, and we'll go back to double check it. Okay? If you guys remember, this is years since that point, so this is every 10 years we're going up by. So our model should have been written as just values of 1. So this should be a 40, an 80, and a 12. Okay? Because it was going up by 10. So this is actually 4 to the right. So we could correct this. Luckily, this value won't change. And it's good that we ran into an error so we know what that looks like. Okay? So, in other words, this model here should be 4, 8, and 12, which is good. That means this is now to the power of 4.
5.0.
What did you get?
5.06.
5.06? Excellent. So this looks like it might be a much better fit. Okay? 5 is still really low at this point. Maybe something like that. Our next year, we're going to go with 8. y equals, and this is our third one, 1 times 1.5 to the power of 8. So 1.5 to the power of 8, 25.6. Great. Okay, so now we're at 25.6. That still looks pretty low for us because this is 50. So this is where 25 would run. So it looks like our model is a little low at this point. Let's see how it picks up at the very end. And our last value should be 12. Y equals 1 times 1.5 to the power of 12. 1.5 power of 12, 129.7. So roughly 130. So again, let's take a look at our model. 130 is maybe here. So this is good. From our exponential model, are we doing a good job of modeling this?
No.
What is happening? We're a little what? We're a bit low, right? So what value in our exponential model should we probably change? The 1.5. We should look for a value that's probably greater than 1.5. And you could try 2. You could try 1.75. And eventually you're going to find a model that's going to look relatively close to what we're getting. Okay? Our goal is to try our best to get as close as possible on this. So that's fine that we didn't get it exact, but it's good that we know that our model is too low, and that's where we'll have to make a bit of a change going through this.